Electricity will power our future, but thousands of renewable energy projects have been put on hold because the U.S. power grid isn't able to handle the increase in energy production. Using state and interstate highway right-of-ways for the installation of new electric transmission lines will increase the capacity, reliability, and resilience of the U.S. power grid, and ultimately aid in carbon reduction. We created a suitability analysis to site electric transmission lines in the highway right-of-way. We did the analysis at two extents, one for the whole state of Minnesota at a 10-meter resolution, and then for a smaller area in southwest Minnesota at a 1-meter resolution. So these are our criteria for the statewide 10-meter analysis. And each criterion was given a cost. And this can be viewed as the cost of doing business. It's a relative measure where 1 is less expensive and 10 is very expensive. So for railroads, we buffered those by 30 feet, and within 30 feet, we gave them a cost of 9, very expensive, because damaging or digging into the railroad embankment can be destabilizing and expensive to fix. For pipelines, within 30 feet of a pipeline, we gave it a value of 8. For fiber, we gave it a 7, because if we were too close, we could cut the fiber and that would be expensive to fix. For electric transmission lines, we gave it a value of 7 because of the danger of working near them. For water features, we need to bore under those, so we gave those a value of 8. Similarly, with the culverts, we gave those a value of 8. For bridges, we have two types. We have rail bridges and road bridges, so we gave those areas a value of 8. For soils, we found histosols and peat. These are expensive soils because they're organic soils and need to be dug out and new fill dirt brought in, so we gave those a value of 8. For urban areas, those are expensive because of the other infrastructures that may be in our project area and underground. And we calculated the minimum construction distance. And for this resolution, we calculated at 30 feet. So any areas of the right-of-way that were less than the minimum construction distance gave a very expensive value. And we didn't make any no-go areas for this analysis. If the feature type was problematic, we just made that criterion expensive. For other criteria we used, we calculated slope. So the lower the slope, the less expensive. The higher the slope, the more expensive. Bedrock at or near the surface, we classified that on hardness and ranked those very expensive. Geology, we also classed on hardness and gave those harder rocks more expensive values. And then for road casing and distance from roads, we want to avoid boring under the roads. So we made roads very expensive as a 10, and areas close to the roads, we also made it expensive. The farther away from the roads were less expensive. We added in trees in the 1-meter analysis only, but I wanted to mention it here. We gave that a value of 7 because of the cost of clearing vegetation. We could add in endangered species. This data is very hard to come by because it's protected. You could add in critical habitat as a proxy for that data. And I didn't add it into this analysis that you'll be seeing, but you could add it in as any other layer and probably get a very expensive cost. So let's take a look at the data. So this is the Minnesota Highway Right-of-Way published by the Minnesota DOT. And this analysis was run only within these right-of-ways. This is the urban areas. These are city boundaries. We have the railroads. I buffered those by 30 feet. We have the pipelines. The electric transmission lines. And in Minnesota, this is mainly above ground transmission. We have the fiber data. We have the water features in Minnesota. We have culverts. This data is spotty because it's published by the counties, and some counties don't publish this data, so we used what we could find. We have bridges. We have two types of bridges, the road bridges and the black and white or rail bridges. For the soils, these are the histosols and peat. And so northern Minnesota will be expensive because of the organic soils. For superficial geology, I've already clipped those to the right-of-ways. We have the green, which is less expensive. That would be the loam, sand, and sediment. And then the darker orange is diamictin, and that we gave a value of 6. We have bedrock. A lot of bedrock in this area will be expensive, and in some other areas too. We calculated the area where the right-of-way was too narrow for construction. So that's this area, and that will be very expensive to build in. Here's the critical habitat layer. Down here is fish habitat. Up here is overlapping values for the Canada lynx and the gray wolf. So you could use this data in your analysis also. So let's zoom in to see some other data. So we have a road going through here, and we can calculate the distance from the road, where close to the road will be expensive and farther away will be less expensive. We can also calculate slope. This is interesting topography here, and it's reflected in the slope, where these darker areas are higher slope and more expensive. So this is the data I used in the suitability analysis. Now let's look at the result. So let's zoom in on St. Cloud. And the blue is the highway right-of-way. And this is the suitability result, where green is less expensive and red is more expensive. Now let's zoom in on this area to get a better look. We can see that the roads are expensive. The overpass are expensive, or more expensive, because we both have the roads and the bridges impacting it. We have a red bit right here, and we can see that we're actually crossing a railroad track. So that's what's causing that to be red. Well, let's see what's going on here. So this is actually overlapping a water feature. That was a marshland. We have histosol soils, and we have diamictin geology. So these three things are adding together to make this a very expensive piece of road to dig through. So we can see how the data that we used in the analysis is reflected in the suitability results. I ran this analysis for all the highway right-of-way in Minnesota. So how do we find the best path through this network of right-of-ways? Our software is able to calculate an optimum path from any origin to any destination. For my origin, I picked an area outside of Fargo, and then randomly picked points along the borders to show across state transmission, and outside of Minneapolis to show transmission to a large urban city. And so these are the optimal paths found out of all of these right-of-ways to these destinations. This is an interesting corridor because 4 optimal paths use this corridor. So it might be worth taking a closer look at this area. Now let's look at this purple route from Fargo to Duluth. I want to use it in a simplified costing scenario just to give you an idea of what's possible. So for this scenario, we used data that we've already used in the analysis, and we created a tool where you enter the boring cost per linear foot, the trenching cost per linear foot, and the cost per vault. So I'll run this and then tell you what's going on in the background. So what's happening is it's taking the optimal path and it's intersecting it with the roads and the water features and finding the length of the crossing. And it's summarizing that and using that as the boring length. And then the rest of the line would be the trenching length. And then it's calculating the number of vaults that are spaced 2,000 feet apart and summarizing those and adding the value for that. So here's the answer in black. So we can see that our optimal path is 282 miles. It found 270 miles of trenching distance. You can multiply that by your cost per unit to get a total cost for trenching. And then it found 11 miles of boring length. You can multiply that by the cost per unit to get the total cost for boring. And it also found 747 vaults spaced 2,000 feet apart, and then you can get the total cost for that. So, and then this is all summarized for a total cost estimate. So this is an example how you can use data that you've already processed for your analysis and the analysis results to help you with your costing scenarios. So now let's look at the 1 meter resolution analysis. I picked a study area, which is a 70-mile stretch of I-90. So let's go ahead and zoom in to see the data. So this is similar to what we've already seen, where the roads are expensive, the overpass are expensive, but we want to understand what else is going on here and what contributed to these results. I like to use other data, including a digital surface model. This is created from the LiDAR point cloud, and you can see the buildings and the trees. So let's zoom in on this area to see what's going on. So we can swipe away the suitability, and we see that this is a highway overpass. So that explains that red area. And what's going on here? So we see we're crossing a creek, so that's a water feature and bridges. So that explains this area. And then we can see the overpass here. So we calculated the optimal path for this study area. That's in white here. We can see that it actually took a little longer route to avoid going across 3 expensive roads. And it tried to stay in the green. So we can swipe away the optimal path. We see it goes quickly through an expensive area, stays in the green, quickly across another expensive area, and then stays in the green. So let's zoom out and go down to the next intersection. So we see that the optimal path is going a little bit farther, but trying to stay in the green and then eventually crossing the road. We see some interesting things here, an interesting pattern here. And I looked for the data to explain that, and that's the urban patch. So this is a city boundary, and we know that because of the additional infrastructure we might encounter, it's more expensive. And so that's what's giving us these straight lines and this extra expense in the southern part of this interchange. So as we move over here, let's look what's going on here. So the road crosses over to get to this long stretch of dark green. So an optimal path is good if we want one answer, one line, but sometimes you want to have options. For example, say you didn't want 2 jogs in this road crossing. So using our suitability analysis, we can create a corridor. And we can see the areas in yellow are less expensive than the areas in the darker colors. So this can give you some flexibility in your decision making. So we've looked at the ways we can understand our suitability results and how it's influenced by our input data. And another criterion we wanted to look at was vaults. So it's very easy for our software to create points along a line at a specified distance. So these are vaults placed 1,500 feet apart. We can also do 2,000 feet apart. And this is the data I used in the costing analysis, and this is very easy for us. We also have another tool that can find optimized locations for our vault, and we can see them here. So this tool takes parameters of the size of the area you're trying to find, which would be the size of the vault, and the distance between these regions, and optimize these locations for you. And we have another one here. Now let's move on to another requirement, which is creating the cable and duct box. I was given this diagram, and we can create this using the optimal path. So I can buffer the optimal path to get 2 cable lines, and I can also buffer the optimal path to get a 50 by 70 centimeter duct box. And later I can lower the data 120 centimeters to get it underground. So let's take a look at that. So this is our optimal path, and we can buffer that to get a 70 centimeter box. And then we can buffer it again to get 2 cables 30 centimeters apart. But we want this data to be underground. So here we have the cables, and the blue is the highway right-of-way, and this is near the Minnesota border. So we want to look at it in 3D, and we want to look at it underground. So here we have the cables and the duct box underground in their accurate X, Y, and Z location. So finally, our last criteria is vegetation clearance. We know that we need a 50-foot clearance above our cables cleared of large vegetation. We can use a LiDAR point cloud to understand our environment and to see our vegetation. And we can create a box using the optimal path above our cables to find the clearance zone. If we fly farther down the street, we can see that we have some vegetation encroaching into our clearance zone. So we know that we'll have some vegetation clearance for our project. So I've shown you some tools that you can use in your planning process to put underground electric transmission lines in the highway right-of-way. Thank you.